Should I start?
Yes.
Okay. Good evening to all. Okay, so in the ring theory, one difficult notion we are going to see. You have seen already some in terms of groups. We are going to see in the ring structure also, which is called quotient rings. Okay, so in the groups, we go modulo normal subgroups. Okay, here the corresponding thing is ideal. So we start with a ring, and I is an ideal. Then the cosets, set of cosets of this, additive subgroup of I plus, additive subgroup I plus of R plus are the subsets of the form A plus I. This is usual, okay, where A belongs to the real, the ring element. Okay, this will look like this. The first theorem says just like we know that R modulo R plus modulo I plus is a group structure, which is having a group structure. Here, since it is I is an ideal, this will have a ring structure. Okay, so here modulo means you see, for instance, you think of R equal to integers Z, and you pick some ideal. It may be 10Z. 10Z is an ideal, already we have seen. If we go modulo Z modulo 10Z, what we are doing? We are doing kind of 10 equal to 0. All multiples of 10 we are identifying to be 0. Then whatever comes out the remainder, then it is like a ring structure. We know it, Z modulo 10Z. So here abstractly we are going to see. So the first theorem says there is a unique ring structure on the set of cosets. We denote it by R bar. R bar is nothing but R quotient I. Okay, the quotient ring Armada I, rather correct way. Armada I is the quotient ring, which is denoted by R bar, such that the unique structure, ring structure, you get it, such that the uniqueness coming from this, such that the canonical map means the quotient map. This is called canonical map or quotient map or projection map, whatever you call it. R to R bar, sending any element A of the ring goes to A plus I, the coset. Okay, this pi is a homomorphism here. The kernel of pi is the ideal I, whatever we started with. So first we prove this. We want to give a ring structure. Already we know this is a group structure is there under addition, this quotient addition. So R bar contains what kind of elements? It's all cosets, A plus I, where A runs through all the elements of the ring. You take any two cosets, we add two cosets in this way. So what is that? A1 plus I, A2 plus I are two cosets in R bar. Then A1 plus I addition now. Addition with respect to, here this addition we are defining in R bar. Okay, but the point is all plus plus is similar for us, kind of, but the point is here it changes. So A1 plus I plus A2 plus I is same as we define. This is the addition. Addition, how we define? A1 plus A2. This A1 plus A2 is a ring addition and the coset, corresponding coset. Similarly, we define multiplication this way. The A1 plus I times A2 plus I is same as A1 times A2. Here, a ring multiplication, the coset there. This product, first of all, see, already we know it's a group because group theory. So here we are defining something new is product. Whether this product makes sense or not, we have to check. Makes sense in the sense the definition is kind of, because you see cosets, a number of representation will be there, but all kind of leads to the same or not. Okay, that's what we are checking. So first you take one element, B1 in first coset, B1 is same as A1 plus R1. B2 is same as A2 plus R2. For some R1 and R2 belongs to that ideal I. We multiply. Now it is a kind of, you see, now it is a ring elements kind of, because B1 we write it as a ring element, B2 write it as ring element, B1 times B2 we can multiply using the distributive law or associativity law. So when we see that B1 B2, it is equal to A1 times A2 plus A1 times R2, A2 times R1 plus R1 times R2, where R1, R2 coming from the ideal element, A1, A2 is a general element of ring. Therefore, the second, third, fourth, all the elements lie in ideal by definition of ideal. Therefore, the sum is in the ideal. Therefore, this B1 times B2 is in fact as a coset, B1 times B2 plus I is same as A1 times A2 plus I. Okay. So even if we take two different representative, the product is deciding the same coset. Okay. So therefore, this product, whatever we have defined, is a well-defined thing. So with these composition laws, you can indeed check it is R bar is a ring. With unity, here unity is the unity in R plus I, the coset defined by the unity in R. So now, so kind of this is defining a ring structure R bar. We have to check with respect to this particular definition of ring structure, this pi is a ring homomorphism or not, the projection map or canonical map. Okay, so the canonical map is pi from R to R bar defined by pi of any element of ring goes to A plus I, the coset A plus I. So just we check three properties, which is trivial from the definition itself. Okay, so the pi is a homomorphism, and then kernel of pi is nothing but set of all elements where pi is from R to R bar. So set of all elements A in R such that pi of A goes to zero element in R bar. What is zero element in R bar? That is nothing but I. Okay, so the pi of A is nothing but A plus I equal to I. It means A belongs to the ideal I. So therefore kernel of pi is precisely I. Okay, so R is a ring and I is an ideal. We looked at the quotient ring R mod I. This is a ring structure. I mean, we looked at the quotient group, the additive group, and then we put a ring structure to this. Okay, and this ring structure is unique in terms of the projection map. Okay, uniqueness is because of the projection map. Projection map goes to this definition only. Pi of A goes to the coset. Okay, this is we have just put a ring structure to the quotient ring Armada. Okay, some mapping property of this quotient ring. Suppose I have two rings R and R prime, and F is a ring homomorphism from R to R prime, such that the kernel of F is I. And this ideal I is contained in R. Okay, so since map is going from R to R prime, let J be any ideal in R such that J is contained in I. So it is sitting inside the kernel, which is needed. Okay, so then we look at R mod J. R mod J we are looking at. See, R mod J is a ring R bar. We are writing is a R bar. Okay, so what we are asserting is there is a unique homomorphism. So first of all, what we have, how many homomorphism we have? R to R prime, we have a ring homomorphism F. Once R mod J is given, R to R mod J, I have another homomorphism, which is called the projection map pi. Okay, this is the one making it unique to the ring structure R mod J. Okay, now what is the claim is? The claim is that there is a unique homomorphism F bar from R mod J to R prime. Okay, such that this happens. This diagram is commutative. But what does this mean? It means if you compose, I mean, rather R to R prime, if you go, that is same as saying that R to Rj, R mod J, and R mod J to R prime, you can go. These two maps are one and the same. After composing pi with F bar, this is the same as F. Okay. And when you see this, we have taken J is any ideal contained in I. Suppose when J is same as I, then what happens is R mod, the F bar of R mod J, the image under this F bar, this is isomorphic to image of R. That's what the claim is. Okay. Okay. So what we have to define, we have given two maps. One is F from R to R prime, ring homomorphism. And another map is R to R mod J, that is pi. The projection map, any element A goes to A plus J, the coset A plus J. That is what pi is. So we want to we define a map F bar from R mod J to R prime. Okay. This is what we want to define. To define a map from F bar from R mod J to R prime, we need to define any element in this R mod J. Any element will look like A plus J. F bar of A plus J we need to define. Okay. So F bar of A plus J, we consider A plus J for some. So you take any coset A plus J. Pi of A is nothing but A plus J by definition of pi. Okay. Therefore, what we want to define F bar of is therefore F bar of A plus J is same as F bar of pi of A. Okay. For any A inside the ring R. But what we want to prove? We want to prove it is nothing but F. Okay. That is the assertion we want to. Therefore, there is no choice other than defining like this. So, okay. F bar of pi of A is same as F of A. We want to define. Whether first we are defining F bar. How we define F bar? F bar of any A plus J, the image will be just F of A. F is given to us already. A is an element of the ring R. Therefore, F of A is given to us. Therefore, F bar of A plus the coset A plus J is same as the image of A under F. Okay, we define like this. This is the map for F bar we are defining. First, when we define whether it is really a map or not, we have to check. It means, so, I mean, one element should not go to two, one element should not have two images. That's what we want to check. That is a well-definedness. So, one element, we take A1 plus J, two cosets, we take two representative F of A2. We want to prove that. Okay. So since
the screen is not visible now. Ah, come. Yeah, came, sir.
Okay. Now it's clear? Okay.
Yes, yes, it is clear.
Yeah. So we have taken one coset with two representation. Okay. So we want to say that the image F of A1 is same as F of A2. This will prove the well-definedness of this map F bar. So since A1 plus J, the cosets are same, it means A2 belongs to A1 plus J. Okay. That means A2 can be written as A1 plus R1, where for some element R1 inside J. Since J is contained in I is nothing but the kernel of F. We see that F of A2, F is a ring homomorphism. F of A2 is same as F of A1 plus R1, which is same as F of A1 plus F of R1. F of R1 that has to be 0 just because R1 belongs to J, and in terms of and hence it belongs to I, which is nothing but the kernel of F. Therefore, F of A2 is same as F of A1 as desired. Okay, so we have defined F bar. F bar, image of F bar is same as F of A, the image of A. Okay, image of F under F, image of F of A. Okay, F bar is therefore well defined. What we need to check? We need to check it is a ring homomorphism and satisfying this property. The satisfying this property, F bar and the pi composition F bar is same as F. That is the way we have chosen. Therefore, it is enough to prove just it is a ring homomorphism. Just it is a matter of just checking F bar of A1 plus J plus F bar of A2 plus J. This is same as F of A1 plus F of A2. F is a ring homomorphism, therefore F of A1 plus A2. That is same as F bar of A1 plus A2 plus J. Same ditto for the multiplication. The unity F bar of 1R plus J, which is nothing but the image of 1R prime, 1R under F. Sorry, this is R prime. This is same as 1R prime as desired. Just it is checking. Okay. So what we have proved. So F is any ring homomorphism from R to R prime, and J is an ideal contained in the kernel of F. That is more important. And if we take the projection map from R to R, R mod J, then we can get a map from R mod J to R prime. Okay, satisfying the property that map, the pi composed with that map is same as the given F. Okay, now we want to prove when J equal to I, the image of R mod J under F bar is isomorphic to image of R under F. Okay, this will pop up once more in the usage. Just it is trivial, but I am writing the proof. F is given R to R prime with the kernel F is I. Therefore, R modulo kernel F is isomorphic to F of R, the image of R under F. Pi is given already from R to R mod J. The kernel pi is nothing but kernel of pi. If you calculate, it is nothing but J. That we have already calculated. This is contained in I, which is equal to kernel F. What is given? Given as I is same as J in order to prove this second assertion. So it means kernel of pi is same as kernel of F because I is equal to J. I is equal to J. So, okay, these two kernels are same. Therefore, R modulo kernel pi is isomorphic to F of R, but R modulo kernel pi is nothing but R bar. Therefore, F bar of R bar is isomorphic to F bar of, because R bar is same as isomorphic to pi of R. So F bar of pi of R, but this F bar of pi of R is same as F of R only. Why? Because of the definition. I mean, what we have proved in the first assertion. F bar, the pi composition F bar is same as F. Okay. This we will use it once more. In the usage, it will be clear how this is kind of coming. Okay. Okay. Now we are okay. So whenever first what we did, we defined some ring. Then we define some subsets which has a structure as a ring, that is called subrings. Once we define rings, subrings, then we define the kind of subsets which are ideals. Okay, this is what we have done. Now, given a ring, hello, yes, given a ring and ideal I. Now we define another new ring called the quotient ring, Armada. Okay. So in the Armada, this is a ring again. We want to understand what are the ideals in this Armada. Okay. So this is what described here. In fact, Armada I, the ideals of Armada I and the ideals, some set of ideals in R is in bijective correspondence. Okay, that is what this proposition correspondence theorem says that. Okay, what kind of ideals? Now we are looking at the ideals in the quotient ring. We want to understand the ideals in the quotient ring. That understanding coming from the already ideals in the ring itself, R itself. Okay. Okay. This kind of describes that, this particular correspondence. This is really useful later. So what is given? We have given a quotient ring R mod J. It means J is an ideal of R. R is a ring. Okay, and pi is the canonical map or quotient map or whatever the projection map. R to R bar. Okay. So now we consider two sets of ideals. One is set of all ideals I in R which contains J, because J is already inside R. You collect all those ideals in R which contains J. So for instance, if we take in integers, suppose 10z. Okay. If we take 10z, can you tell me how some ideals containing 10z? Anyone?
Z.
No, that is trivial. We don't need that.
2Z and 5Z.
2z, 5z, any other ideals possible?
No.
What is your intuition says?
There are only 4, right?
No. Anyway, zero ideal doesn't contain anyway this 10z. Okay. So z contains 10z, 2z, and 5z. These three ideals at least you have told. Any more
10Z
ideal is
itself.
possible?
10Z
No.
itself.
Yeah, that is okay. Oh, that's the way you look at it. Okay. Okay. So at least we could kind of collect. This is an non-empty set. Okay. So now we are looking at in the quotient ring. What are all the set of all ideals in the quotient ring? Okay. This particular, this first we consider all the ideals in R which contains J and set of all ideals in the quotient ring. These two sets have bijective correspondence. How bijective correspondence? You take any ideal in the first set and apply the projection map pi of I. That will be ideal in R mod J. Okay, and you take any ideal in the R mod J quotient ring. Then look at the pre-image of that ideal in R. That is going to be ideal which contains J. Okay, in R. Okay, this is the correspondence. This correspondence is bijective. Okay, that's what the first claim. The second claim, it says, if I is the ideal corresponds to ideal I bar in the above in the above bijective correspondence, I goes to I bar. Suppose these are the ideals. Then R mod I, the quotient ring, is isomorphic to R bar mod I bar. Okay. This is called, I guess, the second or third homomorphism in the group, if you look at it. Okay. So this I is an ideal corresponds to the ideal I bar in the above correspondence. Then you look at the quotient ring R mod I and look at the quotient ring R bar modulo I bar. Okay. These two are isomorphic. This is what we want to prove. Okay, first we want to prove the bijective correspondence. So in order to prove bijective correspondence in this way, I goes to pi of I bar goes to pi, the pre-image of pre-image of I bar in under pi. Okay. So first we have to check that I goes, the pi of I is an ideal or not. And the pre-image of I bar is an ideal in R or not. First we have to check that. Okay, pi is a projection map. A goes to A plus J, the coset. Okay, it's a ring homomorphism. Already we have proved. Okay, so I going to, the pi of I is an ideal or not? Anybody can say? First of all, in group theory, first of all, I is a subgroup, right? I is a additive subgroup in under R plus. Therefore, and I have a homomorphism, group homomorphism under R plus, that is pi. Therefore, the image of I under the group homomorphism is a subgroup, right? That is group theory knowledge. Okay. Now we want to prove it is ideal. Okay. Similarly, the pre-image of a group, whether it is going to be or not, the same way. Okay. In order to prove this theorem, what we need to prove is, okay, there are three conditions. I is ideal in R. Oh, I have written wrongly. I contains J. Okay. This okay, the first if I is an ideal in R such that I contains J, then pi of I is an ideal in R bar. Okay, here such that the containment is not really required in order to prove just ideal. The image of an ideal is under the ring homomorphism is an ideal again. So pre-image of ideal under the ring homomorphism, again it is ideal. The first two statements is generally true. We don't need any condition. Okay. The next statement, for that only we need I is containing J is required. Okay. So what the third statement says, you start with I, you apply pi, okay, pi of I, then you look at the pre-image, you get back I, which is same as saying first start with the I bar and another condition. What it says, you start with I bar, apply the pre-image, look at the pre-image of under the pi homomorphism, you will get pi inverse of I bar, and apply pi, you will get back I bar. Okay, these three statements put together, it gives the bijective correspondence. Okay, is it clear or not? You check. This bijectiveness comes only from this third statement. Okay, and then as a byproduct, we will prove the second statement also. Okay, first we want to check the pi of I is an ideal and pi inverse of I bar is an ideal. Okay, pi inverse here, it is a pre-image. Okay, it's a pre-image, it's not an inverse map, it's a pre-image. Okay, I is an ideal. To show that pi of I is an ideal, first note that pi of I is a subgroup. This is what I just said. Yeah, if little pi is little phi is the group homomorphism G to G bar, G prime, then phi of G is a subgroup of G bar. Okay, that's just by the definition of group homomorphism. Here we need to check to prove pi of I is therefore it is a pi of I is a subgroup, additive subgroup of R bar. Okay. So we want to prove the ideal. Ideal means only one, the multiplicative structure we have to prove. You take any element in the ring R bar and any element inside the subgroup A bar. A bar is pi of I. Okay, A bar belongs to pi of I, and this multiplication should be inside pi of I. That's what we want to prove. Okay, R bar belongs to capital R bar, and that it means R bar we can write it as pi of R. Why? R bar we can write it as pi of R because pi is a surjective homomorphism from R to R bar. Okay, capital R to capital R bar. So therefore, R bar, little r bar can be written as pi of small r for some element R inside capital R. And A bar is already belongs to pi of I only. Therefore, A bar can be written as pi of A for some A in I. Okay. So therefore, we multiply R bar times A bar inside R bar, capital R bar, okay, R mod J. This is same as pi of R times pi of A. Pi is a ring homomorphism, therefore pi of R of A, which is same as saying that R A whole bar. Okay. So since R belongs to capital R, A belongs to capital I, RA belongs to capital I because I is an ideal. Hence, RA bar, see, RA bar, we write it like pi of RA. So RA already belongs to I, therefore RA bar in the image of I, under pi. Okay, just straightforward. Here we never used I contains J. Okay, same way in the other also, but okay. So second one, what we have to prove, the pre-image of I bar is an ideal. Okay, we are going to do it slightly different. We are not going to check whether it is an ideal or not, but what we are, suppose if I don't want to check some subset is an ideal or not using the proper, I mean definition of ideal, but I want to prove it is an ideal. How do I prove that?
To show the kernel of some homomorphism.
Ring homomorphism. Okay,
Ring.
kernel of ring homomorphism. That's what we are going to do. Okay, so we are defining a canonical map. See, R bar is already ring. I bar is the ideal in that ring. Therefore, I can define the projection map again for this particular ring R bar. So phi is a projection map or canonical map from R bar to R bar modulo I bar. Okay, it's a canonical homomorphism. It means sending any element little r bar goes to the coset R bar plus I bar. Okay. Already I have another canonical map pi from R to R bar. Okay. So therefore I can compose this pi. I can compose pi with this phi, so that I can get a map from R to the quotient ring R bar modulo I bar, which is a ring homomorphism because each one is a ring homomorphism. Phi is a ring homomorphism, pi is a ring homomorphism, therefore the composition is a ring homomorphism. Pi is surjective because it's a canonical map, and phi is also surjective because it is canonical map, therefore the composition is also surjective map. Okay. Oh, here another typo. Kernel. So we have defined a ring homomorphism, the pi composing with phi, which is going from R to the quotient ring R bar modulo I bar. Okay, we want to compute. Already it is a surjective homomorphism. What we have to compute the kernel of this particular ring homomorphism. So therefore, what should I have written? Kernel of the composition map phi composition with phi. Okay, that is same as, that is by definition set of all elements in R such that under the composition it goes to zero element in that quotient ring. It means zero element in the quotient ring is nothing but that ideal I bar. Okay, therefore pi composition with phi of A contained in the ideal I bar. That means that the pi composition with the phi of A is same as phi of A plus J. Phi of A plus J inside the ideal I. So this means, okay, phi of A plus J inside I bar. Okay. So what is phi of A plus J inside I bar? Okay. So the next statement I have written that this is same as saying that pi of A belongs to kernel pi. Why? You see, phi of pi of A belongs to I bar. Phi of pi of A belongs to I bar. What is pi? pi is going from R to, no, pi of A, you keep it. The phi is going from R bar to the quotient ring R bar modulo I bar, right? R bar modulo I bar. So it means phi of A under phi, this statement, first statement says phi of pi of A inside I bar. I bar is nothing but the zero element in the quotient ring R bar modulo I bar. Okay, so that means pi of A belongs to kernel of pi, kernel of phi. Okay, so pi of A belongs to kernel of phi means this is same as pi of A belongs to, what is kernel of phi again? Since it's a canonical map, kernel of phi is same as I bar only. Okay, so pi of A belongs to I bar only. That means A belongs to pi inverse of I bar. That means kernel of the composition map, okay, is same as the pre-image of I bar. That's what we have proved. Therefore, pre-image of I bar is being a kernel of a ring homomorphism. This is an idea. Okay, so once we this particular composition map is already, it is surjective ring homomorphism, and we computed the kernel. Therefore, R modulo that phi inverse of the pre-image is isomorphic to R bar modulo I bar. This, okay, this really proves the second portion, second assertion, if we have this, the third one. Okay, you see, pi inverse of I bar is same as I only because of this 3. If we prove this, once we prove this, the second assertion also will follow. R modulo I is isomorphic to R bar modulo I bar. Okay. Okay. So now we want to prove, to complete this particular theorem, we want to prove the last assertion. Okay. In this last assertion, half of the thing is already, for any map, it is true. So as a set, we are going to prove. Okay, as a set, left side is a set and right side is a set. We want to prove equality. It means it contains, one side it contains, other side also it contains. That's the way we are going to prove. One side is it is clear for any map. It is nothing to do with homomorphism or something. General property of the maps, what we know is pi inverse of pi of I, any set, if it's nothing to do with ideal also. Pi inverse of pi of I contains always I. Pi of pi inverse of I bar contained in I bar. These two are automatic from the map property. Okay. So what we need to prove is the other way. It means in the first statement, what we have to prove, the pi inverse of pi of I is contained in I, and pi of pi inverse of I bar is containing I bar. Okay, this is what we want to prove. Obviously, this second, the B statement B is true when pi is surjective. In fact, that is the first proof we are giving. Since pi is already surjective, what is pi? Pi is the projection map. It is a surjective map. So therefore, this should hold. Why? In more generally, again for any is nothing to do with ideal or something. Any sets, it's true. If phi is a map from X to Y, which is a surjective map. X and Y are sets. Okay. Then Y is always contained in phi inverse of Y. Okay, Y is always contained in phi inverse of Y. Just to take any element Y and apply that there is a surjective. So since phi is surjective, there is a element X inside X such that Y equal to pi phi of X. Sorry, here pi nai phi of X. Phi, that means phi inverse of Y, the pre-image of Y containing X. So therefore, when I apply once again phi, I will get back my phi of X, which is Y. Okay. So this is general. Once the map is surjective, this is also automatic. So finally, we are going to use the ideal and ideal containing J, everything we are going to use only for this property. What what we prove that pi in the pre-image under pi of I contained in I. In order to prove that, we need to use our ideal property as well as the ideal I containing J. That also we have to prove. We have to use. So let us see. Take any element X inside the left side. Okay. So once X belongs to this left side, that means pi of X belongs to pi of I. Okay. That means there exists Y in I such that pi of X same as pi of Y. Where X is what? X is a general element. Okay. Here it is in R. Because pi inverse of pi of I belongs to R, the general element. Okay. We don't know whether it lies inside I or not. That and all we don't know. What we know, once pi of X belongs to pi of I, we can able to say that pi of X can be written as the image is captured like a pi of Y for some Y in I. Therefore, since pi is a homomorphism, therefore pi of X minus Y is 0. That means X minus Y belongs to J. Oh, for us, Armada J. Okay. This is in the kernel. Since J is contained in I is the ideal, okay, containing J. So J is contained in I, X minus Y also belongs to I. Already Y belongs to I, X minus Y also belongs to I, therefore X belongs to I. This is because of ideal property, the subgroup property. Okay, so therefore, what we started, X belongs to something, and finally we proved that X belongs to I. Therefore, this left-hand side set is contained in I. Okay, only for this. So in order to prove all three properties, only one place we have to use so that I is containing J. Though again here it is a typo. Okay, I is containing J. It's a typo. Better you correct it in your notes if you take. This is important proposition. In order to understand the ideals in the quotient ring, we can use the knowledge of ideals, some ideals in the mother ring R. Okay, that's what it says. It's clear, right? You go through it, it should be fine. Okay. Okay. So now we want to look at, suppose you see the quotient rings may look different. I mean, look wise different, but the point is it may be isomorphic to the known ones. How we are going to, in some cases, how we are going to really guess that this quotient ring, abstract looking quotient ring, is isomorphic to the quotient ring, known quotient ring. Okay, we will give one particular recipe first, then we see one example. Okay, so the quotient construction has an important interpretation in terms of relations among elements in R. Okay, so the quotienting, I am quotienting something, it means I am killing something. That's the way I will look at it. It means I am putting some relation into 0. This is the way you should look at it. So in a ring R, suppose we perform a sequence. This is going to be abstractly, first I will tell the recipe, then we will take the example. Okay, so we perform a sequence of operations, say plus, minus, or multiplication on some elements to get some new element A. Okay, if the resulting element A is 0, then we say that the given elements, I mean whatever we operating that operations, given elements are related by the equation A equal to 0. This is what generally. Okay, in R, for instance, R equal to Z in the set of integers 2, 3, 6, we looked at it and we performed some operations. 2 cross 3 minus 6 equal to 0. It means, okay, this is the relation. In the ring Z. If the new element A is non-zero, suppose, okay, we may ask whether it is possible to modify the ring structure in such a way that A is zero. Is true. That equation is true. That is, we can think of this process by adding a new relation in R, which will collapse actually the ring. Okay, well, this is abstractly what is written is, you see in integers, 10 is not a zero element. Okay, if I assume that 10 is zero, then what are all happening in the ring? That is nothing but it is leads to the quotient ring 10 modulo Z modulo 10Z. Okay, that's what abstractly we are seeing. So for instance, here I have taken R equal to Z, and then we have a relation 3 into 4 minus 5 is 7, which is not a zero element in the ring Z. But if we impose the relation 7 equal to 0 on integers, it amounts to working modulo 7 only. Okay, so 7 is 0 means after that 14 is 0, then 21 is 0, etc. Okay. So suppose if we impose, suppose we impose the relation A equal to 0 in the ring R, what are the consequences we can get by imposing this relation in R? So first is, as we saw, any multiplication, any element R, little r by A, which is same as 0 only. A is 0 implies R times A is 0. A is 0 implies B plus A is B itself. So these two consequences together, B plus RA equal to B for every element R belongs to R, B belongs to B, B belongs to R. If we want A equal to 0 to happen, then we need to get this, we will get, if once we declare that A equal to 0, then we will automatically get B plus RA equal to B for every B, every R. Okay. So, okay, what is this? This is same as saying that our theorem really says that, tells that, what is the theorem? Theorem is if you are given an ideal and you look at the quotient ring R modulo I, and pi is the canonical map sending A to the coset A plus I. Okay, the kernel pi is I. Okay, this is the abstract ring, abstract theorem, which actually in this case, what it tells. Okay, this, you see, once I declare A equal to 0, I will get this automatically, B plus RA equal to B. This theorem really says that these are all the things I am going to get, nothing more I will get. Okay, why it is? Okay, this theorem, this abstract theorem is saying that once you declare A equal to 0, this is what you can get at most, maximum. Okay, why it is that? Once I declare A equal to 0, I am looking at, I am fixing B, any element B, and vary R in the set. So I am collecting all the elements B plus RA, where R is varying in this. This is nothing but the coset B plus I, where I is the principal ideal generated by A. Okay. So note that by setting B plus RA equal to B for every R in R is same as equating the elements of this coset. You see, B plus RA equal to B is same as saying that we are equating to one coset only, elements of the cosets. Okay, this is precisely what happens when we pass from R to the quotient ring R mod I. I is nothing but the principal ideal generated by A. Okay, this is what, therefore, okay, the elements of R mod I are the cosets. That's what we have seen, B bar, and the canonical map taking B bar, canonical map carries all the elements of the form B plus RA into the same element pi of B. That is nothing but B bar. So every element B plus RA is going to pi of B. Okay. So A equal to 0, A bar is also 0. So A declared A in R, we declared to be 0. Okay. This in this way, in this setup, really A bar is 0 or not? A bar is 0 just because A belongs to what? It is in the ideal, because ideal is I is generated by A. So it means it is in the, that's what we have killed. I mean, R modulo I, in that, since A belongs to I, it is in the kernel of pi homomorphism. Therefore, A bar is a 0 element. Okay, A bar is a 0 element. Therefore, it is reasonable. So it is reasonable to view the relation A equal to 0 as the quotient ring R mod AR. Okay. So whatever we have studied the quotient ring, this amounts to force a relation in R. Okay, we will see an example. Of course, this A equal to 0, the new element, how we got A? By doing some operation, ring operation with some elements, and we got A. Whether this same thing respects or not, we will check. That is also okay. Note that the element, new element A, was obtained from some other elements by a sequence of ring operations. So, for instance, U times V plus W equal to A, suppose. And we know that in the quotient ring, A bar is 0. A bar, the element is a 0 element in the quotient ring. Okay. Therefore, the left-hand side also should be a 0 element. It should be. But the point is, U is an element of R, V is an element of R, W is an element of R. Therefore, U bar, V bar, W bar, these are all elements of the quotient ring. Okay. When I multiply, we know R bar has a ring structure. When I multiply U bar times V bar plus W bar, I should get back my 0. Okay. That is true. That is true because pi is the ring homomorphism, and pi is defined this way only. U goes to U bar, V goes to V bar, W goes to W bar. Therefore, U plus V plus W whole bar is same as U bar, V bar plus W bar. Therefore, this is really respecting the ring structure. Okay. Okay. This is abstractly I have given a recipe. So we want to know what is the quotient ring. So for that quotient ring, if you are quotienting something, it means that we are defining a new relation in the ring structure, in the ring, given ring R. Okay. This is the way to identify some of the quotient rings to the known. We will start with one example. Okay. The ring is Z of I. Z of I is nothing but the set of Gaussian integers. Set of Gaussian integers will look like A plus IB, where A and B are integers. A and B are integers. Now we look at the ideal generated by 1 plus 3i, and we are quotienting it. Okay, we look at the quotient ring Z of I modulo the ideal generated by 1 plus 3i. What is this? What is this quotient ring isomorphic to known ring? Anybody can make a guess from the previous recipe. Okay, I want to kind of guess what should be the ring. What first the recipe says? This quotient ring is same as by applying some relation, right? What is here? A is what? In this example, what is A?
1 plus 3i.
1 plus 3i. Okay. 1 plus 3i is an element of Zi. I want to put 0. Okay. That's what we should start with. Okay. We will start with. Okay. In Zi, already we have one relation, I square equal to -1. Okay. In Zi, we are quotienting this ideal. This means that we are introducing a new relation 1 plus 3i equal to 0. That is same as saying I equal to 3. Okay. That is same as equal to saying, because just by simplification, it says as I equal to 3. Since I square is -1, we see that -1 equal to I square equal to 3 square, because I equal to 3 I am putting. That is same as saying that 10 equal to 0 in the quotient ring. Okay, that so it is reasonable to guess that this ring is isomorphic to Z modulo 10Z. Okay, now we will prove this. Why it is. Okay, how we are going to prove? We are going to use the unique homomorphism from Z to any ring R. Here the quotient ring R. What is the quotient ring? Z of I modulo the ideal generated by 1 plus 3i. And we will use this homomorphism, and we prove that this is first of all, this homomorphism is this particular homomorphism, whatever the unique homomorphism, this is surjective here in this. Okay, and we look at the, therefore once you know that surjective here, then image of phi is same as the quotient ring, which is isomorphic to Z modulo the kernel pi. So therefore, first we have to compute this. First of all, we have to prove that phi is surjective and kernel pi is same as 10Z. That's all we have to prove. Okay, in order to prove this isomorphism, we use this unique homomorphism, and we first prove that this this homomorphism is a surjective homomorphism, and we compute the kernel pi. Kernel phi is nothing but 10Z. We will prove that. Okay, so we really need to prove phi is surjective, kernel phi is 10Z. Okay, first we prove that phi is surjective. If you want to prove phi is surjective, take any element, and we have to take any element in the quotient ring, and we have to give a map. I mean, we have to get a pre-image to that given element. Okay, so what is the any element? Any element in this ring Zi will look like A plus IB. Okay, in the quotient ring I equal to 3 we know. Okay, so therefore the residue A plus IB modulo the ideal 1 plus 3i is same as A plus 3b. I is in the quotient ring, it is I is 3. Therefore A plus 3b. Therefore A plus 3b, since A plus 3b is an integer, I can always map this phi of A plus 3b to A plus bi modulo this ideal. N inside the kernel, yes?
I don't know, your voice now break it actually. Yeah.
Is it fine now?
Yeah, it's fine now.
Okay, my internet is kind of going and coming. Okay, we want to prove that kernel phi is 10Z, the ideal generated by 10. So we pick any integer inside the kernel pi. That means phi of n is a 0 element. Phi of n is a 0 element in that quotient ring. It means phi of n in the, see, 0 element in the quotient ring means phi of n in the ideal 1 plus 3i. Okay, is a phi of n is in the ideal. But you recall, what is this phi? Any integer. So phi is the unique homomorphism from Z to any ring R. How it went? Any integer n, suppose n is positive. Okay, n will go to phi of n will be look like 1r plus 1r plus 1r n times. If n is negative, then phi of n is same as minus phi of n. Okay, that is no, phi of minus n equal to minus phi of n. That's what the unique homomorphism. So phi of n is in this I, but the point is phi of n we can rewrite it as, okay, again I have written wrongly here, 1 the unit element in that quotient ring. What is that unit element in the quotient ring? 1 plus the ideal, the coset 1 plus, okay, coset 1 plus the ideal. That is the coset. Okay, coset plus coset plus coset plus n times. If you add, that is same as n. N belongs to already ideal. Okay, that is same as n plus this. That is phi of n is inside the ideal means n plus ideal. That coset is same as this ideal. Zero element. Okay. That means n belongs to this. Okay. Here I have written kind of, this is another typo. You have to know. Phi of n is nothing but the unit element in the codomain. Okay. Unit element in the codomain ring. That unit element here in the quotient ring is the coset 1 plus the ideal. Okay. So what we get is the integer n actually inside the ideal. Okay. So therefore n can be written as a plus ib times 1 plus 3i, because every element of this ideal will be any multiple of 1 plus 3i, any multiple coming from the ring zi. Okay. So this, if we just multiplication, when we do, what we get is a minus 3b plus I times a 3a plus b. Okay. So since n is an integer, what we get is there is no I term. Therefore, that term is 0. So 3a plus b is 0. That means b equal to minus 3a. So therefore, n equal to a plus bi 1 plus 3i. But b equal to minus 3a I will put. So what we get is it is like 10a. N is nothing but 10a. So therefore, we started a element in the kernel phi, and we proved that that element is inside 10z. Okay. So therefore, kernel phi is contained in 10z. So since 10 is 0 element in this quotient ring, automatically 10 is inside the kernel phi. Okay. So therefore, kernel phi is nothing but 10z. Therefore, the first isomorphism theorem, this quotient ring is nothing but z modulo 10z. Okay. So this is a recipe in order to know how to find the abstract quotient ring to the known ones. Okay. So there is one more recipe is there. There are two more recipes. So in the coming class, I will continue. With that, I am stopping here. Huh?